Hello and welcome to the preparatory workshop for the foundation courses. This video will be on the completeness and compactness theorems and some consequences. Okay, let's first have a look at completeness. So for the rest of this section we fix a first order language L. If you don't remember what that is, have a look at the previous video explaining the syntax and semantics of first order logic. So first of all, the soundness theorem for the proof system that we described in the previous video says the following. So given a set of sentences, which are thought of as hypotheses, and a sentence, again over the same language, then if S proves P, it follows that S models P. Recall that this simply means that all models of S are also models of P. Okay, so this, first of all, again, tells us something that is reasonably expectable, which is that if a set of hypotheses proves something, then all models of that set of hypotheses should satisfy that sentence. And this can be shown very easily by induction on the lines of a proof. If you want to see more details about this, then I would recommend taking a look at the part 2 logic and set theory notes. It's not 100% important to remember the proof of this right now. Okay, so recall that a set of sentences is said to be consistent if that set doesn't prove false. Now, what the completeness theorem tells us is that if we take a set of consistent sentences, so a set of consistent hypotheses, then it follows that that set has a model, meaning that there's an L structure such that M models S. So it models all sentences in the set S. Okay, so this is, in a way, the sort of backwards direction of the soundness theorem. In fact, the theorem that is 100% corresponds to the backwards is the corollary to the completeness theorem, which we will be seeing in a second. But let's first have a look at this. Okay, so I'll explain a bit the idea behind this because it's something important. Although this is something that you will be taking for granted for all of the foundations courses, and yeah, it's not too necessary to remember this, but in any case it is interesting. Okay, so the idea is that starting from this consistent set of sentences, we use Zorn's lemma to extend this set to one that is maximal and consistent. So what do we mean by maximal? In a sense it is complete. That is that for all sentences P, either P is in our set S1 or the negation of P is in our set S1. And this is an extension, meaning that our original set is contained in S1. Now, I will not explain the details of how this S1 is produced. As I said, this is obtained through Zorn's lemma, which is equivalent to the axiom of choice, and you can find the statement of this in the 6th video. That is precisely on the axiom of choice. But the idea is that somehow we have this set of sentences which is consistent, and we keep adding more sentences so that eventually we get something that is maximal, but we do this in a way so as to ensure that we remain consistent. So we do not just add a lot of things that are potentially rubbish and lead to inconsistencies. Okay, now in this new set, what we do is that for each sentence of existential of the form there exists xp in S1, we add a new constant to the language that is, in essence, it's going to be a witness to the existential quantifier. So we will add this new constant t and add to our set of sentences the formula p, where now x has been, all three occurrences of x have been substituted by t. Okay. Now, this is a new constant. It's not in the original language. So S1 is a set of sentences in an expanded language. Okay, so therefore we obtain an expanded language, this L1 that contains the original language, and a set of sentences in this new language that has witnesses for S1. Now, the idea is that we run through the same process again. So now we extend T1 to some new maximal consistent theory, S2, in the new language, lambda 1, L1. And we add witnesses to S2 to obtain some new theory, which is now in a new language, because we added new constant symbols. And the idea is that we continue inductively. And so eventually we produce a chain of languages, which are just going to be extensions of the original language by new constant symbols, and consistent and complete. By complete, I just mean maximal in the sense above, that either a sentence is in there or its negation is in there, that has witnesses for itself. Okay, so the fact that it has witnesses for itself, it's not 100% trivial, but it's something that you can show for induction. The idea is that if you take some sentence of the form, there exists P, which is in this S dash, it must be that it is in one of the SIs, and because it is in one of the SIs, then in SI plus 1, we can find a witness for it. And now this witness is back in S dash, so S dash has witnesses for itself. Okay, so now we've expanded this language by a bunch of new constants, and we are essentially going to define a structure on the set of closed terms in this new language. Okay, so literally we take the set of closed terms in this new language. It has a bunch of constant symbols, so we get many closed terms, but we need to quotient it by an appropriate equivalence relation, and this is not going to be particularly surprising what happens. So we define an equivalence relation on the set of closed terms. So S is equivalent to T if and only if it is a consequence of S dash, now this new set of sentences in this new language, that S is equal to T. It's not difficult at all to show that this is an equivalence relation. S dash, recall that it is consistent and complete. Okay. And it can then be showed by induction on the structure of a formula, by which I mean that we start with atomics and we move on to full formulas, that P is a consequence of S dash if and only if P is satisfied in M. M satisfies P. Now this model M that we have built on the set of closed terms, quotiented by this relation, is in fact, it's going to be an L dash structure, but L dash is simply an extension of L. So if we just restrict to the reduct of M in L, this structure M prime, it's not difficult at all to show that that M prime now is a model of S as required. So we started with a consistent set of sentences and we have obtained a model. And this model somehow is inductively produced by adding, so expanding our theory to one that is maximally consistent, then adding witnesses back to it, keep doing this infinitely, obtaining a chain, and then building a model on the set of closed terms in this expanded language. Okay, so a direct corollary to the compactness theorem is what is known as the adequacy theorem, which is often just taken to be the compactness theorem itself. And it is precisely the converse to the soundness theorem that I covered before. So it says that if we take a set of sentences and a sentence, then if S models P, meaning that all models of S are also models of P, then P is a consequence of S. S proves P. Okay. And this is not difficult at all to show just from the completeness theorem in the form that I gave it to you before. Why is that? Well, let's try to do the contrapositive. Suppose that S does not prove P, then it follows that if you consider the set S union the negation of P, that must be consistent because it doesn't prove bottom. If it did prove bottom, then S would prove P by the soundness, by the deduction theorem. Therefore, because the set is consistent, it follows by completeness that it has a model. And since it has a model, it follows that S cannot model P. Because if it did, then it would mean that all models of S would also model P, but we know that there is some model of S that models not P. So that's a contradiction. And so we've actually shown the contrapositive, which is what we wanted. Okay, and putting soundness and adequacy together, we get, I guess, what is often referred to as Gödel's completeness theorem for first-order logic, that tells us that if we take a set of sentences S and a sentence P, then S is a model of P if and only if S approves P. Okay. And one point that I should make here, which is something that you should have in mind, though it's not something that, if you want to, you can run through the proof on your own and realize why this is the case, which is that if we start with a countable language, okay, then, in fact, we do not ever need to use Zorn's lemma. So recall that Zorn's lemma is used to go from our original set to one that is maximally consistent, and we keep doing this in this process. If we start from a language that is countable, then, in fact, we can make sure that we can always find something that is maximally consistent without having to resort to Zorn's lemma. Okay. As an exercise that I leave it to you, it's not particularly difficult, and a part of this is basically the completeness theorem itself, is that, okay, fix a set of sentences, then the following are equivalent for this set, S. First of all, that S is consistent, which according to the original definition just means that S does not prove false. Secondly, that there's no formula such that S proves formula P, such that S proves P and S proves the negation of P. And finally, thirdly, that there's some formula such that S does not prove this formula. And finally, that S has a model. So all of these are equivalent definitions of consistency for a set of sentences. And yeah, provided you've shown this exercise, of course, but it's not particularly difficult. Okay, let's move on to compactness, which is very important, and it is something that will be coming up a lot in the model theory course, and it's a very common technique in model theory. So the compactness theorem for first-order logic says the following. Fix some set of sentences, of course in an ambient language L that we fixed, and let this set of sentences be S. Then what compactness tells us is that if every finite subset of S has a model, then it follows that S itself has a model. Okay? If you want to view this in a contrapositive way, if S doesn't have a model, then it must be that there's some finite subset that does not have a model. Okay? Which is good because somehow we can resort to things are somehow, I guess, it's like a local to global kind of theorem. Okay, so let's see a proof of this from the completeness theorem. We'll do the contrapositive again. So suppose that S does not have a model. By completeness, it follows that S is not consistent. Therefore, S proves false. And since proofs are finite, that's by definition, it follows that not all of the assumptions, the hypotheses of S appear in this proof, because proof is a finite set of sentences. Therefore, it follows that there's some finite subset S prime of S, such that this finite subset proves false. And the proof literally is exactly the same proof as above, right? Because that proof only uses stuff that is now in S prime. And by soundness, this implies, or completeness again, if you consider completeness to be the by implication, this implies that S prime does not have a model. Okay, which gives us precisely completeness. Another form of compactness, which is very standard to see, is the following, and it's sort of a straightforward argument why it holds. So take a set of sentences, S, and take a sentence P. Then if S models P, it follows that there's a finite subset S prime of S such that S prime models P. So recall, this is not 100% although it is a corollary and it's not difficult to show it at all, this is not the same statement as the one above, right? The one above just says that things have a model, whereas here we're not only interested in S, but also S sort of modeling something. Okay, let's see a proof of this. It's very straightforward. So suppose that S models P. It follows that S union the negation of P does not have a model. Why is that? Well, if it did have a model, then it wouldn't be the case that all models of P are also are also models of P, which is precisely what this tells us. It follows by compactness in the way that I have stated it above, that there must be some finite subset, S prime, which is a finite subset of S union not P, which does not have a model. Therefore, if you consider S taking away the negation of P and adding it back, because that's literally just S prime, that does not have a model. And therefore, it follows that S prime take away the negation of P models P. Okay, why is that? Because all models of S prime take away the negation of P also satisfy P, because the above, S prime take away the negation of P union negation of P does not have a model. Okay, and this now is a subset of S, right? So S prime take away the negation of P is a subset of S, and this models P as required. Okay, so I'll now continue to some consequences of the compactness theorem. Of course, there are plenty, but we'll just be seeing a few applications of this. Okay, so we say first of all that a class of structures is finitely axiomatizable if the class is axiomatized by a finite theory, so a finite set of sentences. Okay. Now, what I would like to show at the end is that, and this will be the corollary to the proposition I'm about to give, is that fields of characteristic 0 are not finitely axiomatizable over the language of fields. But before showing that, I'll show something, the bit that actually requires compactness, which is slightly more general, which says the following. So suppose that you have a class of structures, which is axiomatized by some theory, by some arbitrary theory, okay? If you know that the class is finitely axiomatizable by any axiomatization which could be it could have nothing to do with T, then it must be that it is finitely axiomatizable by some finite subset T prime of T. Okay. This is not tautological, okay? Because the fact that C is finitely axiomatizable, as I said again, it could be that there's some arbitrary set of sentences, finite, that axiomatizes C. But what this tells us is that if you fix some axiomatization and you know that your class is finitely axiomatizable, then there must be some finite subset of this fixed axiomatization that witnesses this. Okay, why is that? Suppose that we have this finite set of sentences that possibly has nothing to do with T, that witnesses that C is finitely axiomatizable. Okay, since this set S is finite, we can simply consider the conjunction of all the sentences that appear in this set. So let this be phi S. It follows, therefore, that for all structures M is in C if and only if M is a model of phi of S, if and only if M is a model of T. In particular, it follows that T is a model of phi of S. Why is that? Because all models of T are also models of phi of S. Therefore, by compactness, and in particular by the corollary to the compactness that I gave to you before, it follows that there's some finite subset T prime of T, such that T prime models phi of S. And therefore, this finite subset of T is precisely what gives us our finite axiomatization of C. Why is that? Because for all L structures, M, it holds that M is in C if and only if M is a model of phi of S, if and only if M is a model of T prime. And so T prime is this finite subset of T that finitely axiomatizes C. Good. How does that give us what I told you just a minute ago? So, The corollary is that the class of fields of characteristic 0 is not finitely axiomatizable over the language of fields. So consider the standard axiomatization of fields of characteristic 0. That is, we take all the axioms of fields that say that you're an abelian group under addition, abelian group under multiplication, of course, without 0, that the multiplication is distributive over addition, and that, of course, 0 is not equal to 1, okay, so that you have at least two things. And then to say, or at least one way of saying that you have characteristic 0, is to add infinitely many sentences, each one saying that 1 plus 1 plus 1 n times is not equal to 0. And I add these sentences for all values of n. Okay. Recall that why does this capture fields of characteristic 0? Well, if you don't have characteristic 0, then it must be that it's p for some prime. Therefore, it follows that one of these things are, one of these sentences is true of our fields, but our theory forces that none of these is true. And therefore, it follows that any field that models this set of sentences cannot have a non-zero characteristic, so it has 0 characteristic. Okay, but now the statement, the proposition that I gave to you before, would tell us that if there was a finite axiomatization of the class of fields of characteristic 0, it would have to be a finite subset of the axiomatization I gave you just before. But notice the following: any finite subset of this can only contain finitely many of these sentences phi of n. Therefore, if you take a prime which is larger than the maximum of all the of all the n's where the sentences phi of n appear in this finite subset, it follows that the finite field of order p would be a model of this finite subset. But clearly, this has characteristic p, which is non-zero. Therefore, there's no finite subset of this theory that axiomatizes our class, and therefore our class is not finitely axiomatizable because of the proposition that I gave to you before. Okay, this is an application of compactness. And this is how often you would show that things are not finitely axiomatizable. Supposing that you'd had any axiomatization that your favorite one, then showing that there's no finite subset of that one would suffice because of the proposition I told you. As an exercise, I leave to you the following, which is, well, not showing that something is not finitely axiomatizable using compactness, but in fact showing that something is not axiomatizable at all. So, as an exercise, show using compactness that the class of groups with an element of infinite order is not axiomatizable over the language of groups. Okay? And as a hint for which kind of structure you should consider and have in mind, so consider Q mod Z, so Q quotient by Z as a group with addition. Okay. Let's see two more consequences of compactness. Well, I guess one of compactness, the other of completeness. And these are the Leuwenheim's-Kolem theorems, which are very important in model theory. But unfortunately, we're not going to see them in their full power. You will see those in the model theory course. But nonetheless, just from compactness, we can actually obtain sort of weaker forms of these. So the weak upward Leuwenheim-Kolem theorem would tell us that if you take any theory with an infinite model, then it must be that our theory has, in particular, a model of uncountable cardinality. Okay? Why is that? We haven't talked about cardinalities yet. This is, by the way, in video 7. But by uncountable, just consider the same size as the reals. Okay. So how do you show this? So simply, what you can do is you can expand your language using uncountably many constants. So these constants are Ci, where I ranges over an uncountable set, say the reals or any set I, for instance. And now we're going to expand our theory. So we consider T prime, which is our original theory union, a bunch of sentences that say that these constants, Ci, are not equal, so Ci is not equal to Cj for any choice of I and j over our indexing set. Okay, well, is this satisfiable? Well, clearly every finite subset of T prime has a model. Why is that? Any finite subset will only make reference to finitely many of these constants, and therefore what we could do is just take this infinite model of T, which we know to exist by assumption, and expand it with finitely many, by interpreting these finitely many constants that appear in this finite subset. Okay, and this would give a model of the finite subset of T prime. And again, this can be done because we know that T has this infinite model. And therefore, by compactness, this implies that T itself has a model because all finite subsets of it have a model. This model will clearly be uncountable, right? Why is that? Because T prime, this new theory, says that all of these constants are interpreted as different elements. Therefore, it must be that there are uncountably many elements in our domain. If you consider the reduct of this, so the restriction in the original language, this is a model of the original theory whose size is uncountable. Okay. There's also a downward analog. So this is often called upwards. Why? We simply know that our theory has an infinite model, and we go to models of, in fact, any infinite cardinality that we, well, larger than any infinite cardinality that we want. Okay. So why am I saying larger? Because, okay, of course, it could be, say that this is, our constants are indexed by the reals. It could be that the model that we get through compactness, what we know is that its size will be at least as large as the set of reals. It could be even larger. So that's why the idea is that it's upwards. For every kind of infinite cardinal, we can always find some model that is larger than this cardinal. The downwards theorem, what it tells us is that if we have a countable language, at least in its weak version, that if we have a countable language and a set of sentences over this language, then if this has a model of any size, then it must have a countable model. So, excuse me, this was a mistake. This should say a countable model. Okay. Why does it have a countable model? Well, if T has a model, then by completeness it must be consistent. And therefore, if you run through the proof of the completeness theorem, assuming that the language is countable, then the model that we obtain is in fact countable itself. You just have to verify this through the proof that I gave to you before. Okay, both of these theorems are very important in model theory. The versions I've given to you now here are sort of weaker than the proper ones, but you will be seeing the proper ones very soon in the model theory course.